Hi all physics lovers, let's see this question of Irodov. Question number 3.27. Question states, space is filled up with a charge with volume density rho is equal to rho naught e power minus alpha r cube. Well, rho and alpha are positive constants. R is the distance from the center of the system. Find the magnitude of the electric field strength vector as a function of R. Investigate the obtained expression for the small and large values of R, i.e. at alpha r cube is much smaller than 1 and alpha r cube is much greater than 1. So given in the question is the volume charge density in the space, like there is a volume charge density something like this, and something like this. And this charge is spread in the volume all over the space, not uniformly with some variation. The center of the volume charge density is somewhere here, and at a distance small r from here, like at a distance small r from here, at this distance, rho is this, given by rho is equal to rho naught e power minus alpha r cube. So we have to find the electric field strength at a distance r from this center. So what I'll do, I'll make a sphere of radius r, whose center is at the center of charge, something like this, and I will find electric field at this point here. So I think in the previous question also I told that if the charge distribution is spherically symmetric, what do you mean by the spherically symmetric? That it depends only on the r, not on theta. Then to find electric field at any general point, what you can do, suppose this is spherical charge distribution, and if I want to find the electric field at this point, so make a sphere of radius r whose center is at the center of charge. Clearly the whole space of charge can be divided into many shells. Some shell would be inside that region, inside that sphere, some shell would be outside that sphere, like this. I'm not making the complete shell, and the thickness of the shell is so small that at all these points, this is a function of r. At all these points there is only one r, so rho is a constant. Here also rho is a constant, so that is a kind of a concentric shells of uniform density. The density at a particular shell is a constant. So to find electric field due to a uniformly charged shell, the electric field inside the shell is 0, and outside the shell, to find electric field at outside point, what we do, we put the all charge at the center. So here, if I have to find the electric field and all such shells, for all such shells, this point would be the interior point. And to find the electric field at this point, because all the shells within this point, what I have to do, I have to calculate the total charge here, total charge within that shell, put the whole charge at the center, and then apply the formula for the point charge, that is the kq by r square. And for all shells outside that point, this point would be interior point, and electric field due to any uniformly charged shell at an interior point is 0. So basically, if I have to find the electric field at this point, what I need to do, I need to calculate the total charge within a sphere of radius r. And then I'll put all the charge at the center and then apply the formula for the point charge. So my formula, my answer is going to be simply E is equal to, E is equal to KQ divided by R square, where the Q is the total charge within the sphere of radius R. And then to calculate this charge, I will make element normally as we do. I'll take an shell whose radius is, say, x and thickness is dx. So volume of this shell dv is equal to 4 pi x square dx. And charge contained in this shell is the volume charge density of that shell into 4 pi x square dx. And at a distance r from the center, this is the charge density. So at a distance x from the center, so volume charge density would be rho naught e power minus alpha x cube, and then we have to multiply by 4 pi x square dx. To integrate this thing, we'll have to put some substitution. The substitution that I'll take the substitution alpha x cube is equal to, say, some u. So then what will happen? Then 3 alpha x square dx, 3 alpha x square dx will become du. So in place of x square dx, I'll put du by 3x, 3 alpha. So coming back to that dq, this dq, so that dq will now become 4 pi, this 4 pi rho naught, 4 pi rho naught I have taken here. E power minus alpha x cube will become e power minus u. And x square dx is how much? Du, and divided by how much? 3 alpha. So this what I've got. And then to integrate this, I am not putting the limit right now, just because I have to change the limit from u to r again. So if I integrate it, I will get q is equal to 4 pi by 3 alpha, and rho naught is there. E power minus u, this integration will be minus 1 by u e power minus u. And not put the limit. And then let me put it back to what I assume, the value of u. 1 minute. This will be not minus u, that will be only minus 1. So this will be minus of e power minus u. So minus 4 pi by 3 alpha. I can put the value of u here only, right? Because what I assume, I assume u to be alpha x cube. So in place of u, I can put alpha x cube, and now I can put limit here. The x will go from 0 to small r. So if I put the limit, upper and the lower limit, so we are going to get how much? This is 4 pi by 3 alpha rho naught, and that will be 1 minus e power minus alpha r cube. So this is the total charge. So put that total charge here. I can put the value of k also. K is equal to this is basically q upon 4 pi epsilon naught r square. So if I put it here, so I will get E is equal to all the thing after putting, we'll get rho naught by 4 pi will get cancelled here, and there will be epsilon naught 3 alpha. So 3 epsilon naught alpha and 1 minus alpha r cube, and divide by, it's not 1 minus alpha r cube, 1 minus e power, 1 minus e power minus alpha r cube, and divided by that r square. So this is the expression for the electric field. And then we have to see some approximation. Oh, let me go to the next page. What I've got, E is equal to rho naught by 3 epsilon naught alpha into 1 minus e power minus alpha r cube, divide by r square. And we have to investigate for this expression what happens for the alpha r cube much greater than 1 and much smaller than 1. So in fact, I'll write for the e power minus alpha r cube for 2 cases. When alpha r cube is much smaller than 1, for the e power minus alpha r cube, I'll use the expansion of e power 1 plus x. So this e power minus alpha r cube, because this is very small, can be approximated to 1 minus alpha r cube. So 1 minus e power minus alpha r cube can be approximated to alpha r cube. And when alpha r cube is much greater than 1, so e power minus alpha r cube you can write as a 1 upon e power alpha r cube. And now alpha r cube is much greater than 1, so denominator is a very large number. So 1 upon very large number is a very small number, so that will be approximately 0. So for case 1, alpha r cube much smaller than 1. This 1 minus e power minus alpha r cube is approximately alpha r cube. So electric field expression will become rho naught divided by 3 epsilon naught, and this alpha will get cancelled, and in the denominator there is only one r cube. In the denominator there is r square, and in the numerator r cube, so that will be rho naught r by 3 epsilon naught. And case 2, when alpha r cube is much greater than 1, so this whole exponential term will be 0. Then E would be approximated to rho naught divided by 3 epsilon naught alpha r square. This is the required expression. Thank you.